Good afternoon and welcome everyone. My name is Sierra Lamonaco and I am the Alumni Relations Officer with the Faculty of Applied Science and Engineering and the Program Lead for the Skule Lunch Learn series. I would like to thank all of you for tuning in today for our last Skule Lunch Learn presentation of the 2023-2024 program season. With alumni tuning in from all over the world, we have guests joining us today from across Canada, Hong Kong, Jamaica, Kenya, South Korea, Switzerland, the United Arab Emirates, and the United States. So welcome. Before starting today's presentation, I wish to acknowledge this land in which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to many Indigenous peoples from across Turtle Island, and we are so grateful to have the opportunity to work on this land. Now, I hope each of you is excited for today's presentation, as our guest speaker is Professor Alison Olechowski, and she is an emerging leader in the engineering education research. Professor Alison current research on the implications of in-program collaborative tools on product design aligns very closely with U of T's commitment through the Defy Gravity campaign to drive scientific discovery and create a reservoir of ideas to meet tomorrow's challenges. Now, a quick housekeeping item at the end of today's presentation, we will have time for a formal Q&A. Questions can be shared in the bottom of your screen, right there where the Q&A button is. So for the individuals who submitted their questions during the registration period, thank you for passionately exploring your curiosities and enriching our discussion today with your insightful questions. Now, without further ado, I am pleased to introduce my extraordinary collaborator and MC for today's presentation, Laurie Hevela. Laurie is someone who exemplifies unwavering dedication and authentic collaboration in every facet of his involvement at U of T Engineering. Laurie is not just an electrical engineering 65 graduate. His efforts as an active volunteer, a generous donor, and a trusted collaborator defines his commitment to creating inclusive and supportive environments within our community. For over a decade, Laurie has served as the chair of the Skule Lunch Learn program, devoting his time and expertise to fostering an atmosphere of innovation and knowledge sharing within our community. So with that, please join me in welcoming my remarkable Skule Lunch Learn partner, Laurie Hevela, who will now introduce today's speaker. Thank you.
Thank you, Sierra, for your very kind introduction. It is indeed my pleasure to welcome our guest speaker today, Professor Alison Olechowski. Dr. Olechowski is an assistant professor in the Department of Mechanical and Industrial Engineering here at the University of Toronto. She completed her PhD at the Massachusetts Institute of Technology, studying engineering technology management. She completed her BSc in engineering at Queen's University and her Master of Science at MIT, both in mechanical engineering. Her current research focuses on engineering design. In particular, her group investigates how new technologies can best be used to improve the process and outputs of engineering design and new product development. Her lab is supported by grants from Canada's national funding agencies, the Alfred P. Sloan Foundation, and industry partners, including computer-aided design users and providers. And now, without further ado, please join me in welcoming Professor Alison Olechowski.
Great. Thank you so much, Laurie and Sierra, for those introductions. I'm really pleased to be speaking with you all today. In fact, I'm joining from my office in the MyHall Center. I think hopefully you can see my cursor on the screen here, but that's the building on the right side. And I think one of my windows is visible looking out north up towards Bloor. So it's a beautiful blue sky day here in Toronto, a good day for giving a talk, I think. Great. So indeed, I'm an assistant professor in the Department of Mechanical and Industrial Engineering, but also in one of the University of Toronto Faculty of Applied Science and Engineering's newest institutes, the Institute for Studies in Transdisciplinary Engineering Education and Practice. That's ISTEP. And if you haven't heard about ISTEP before, it's an institute that brings together folks who care about engineering education, engineering practice, engineering communication, engineering design, I'm probably missing some interesting engineering ands, but it's great to be working with those folks too. And so I've already been introduced for the most part in terms of my background. I did go to Queen's for my undergrad. Please don't hold that against me. I want to make a note of the fact that my interest in product design and development was actually sparked when I worked at Research in Motion, the company that made Blackberries. So I grew up in Guelph. During my upper years at Queen's, I was looking for an internship. I got really lucky. I got hired at RIM, which was like a cutting edge company at that time. Everybody had Blackberries. And then I was lucky. I got offered a job there, went to Waterloo for the summer, for 3 summers actually, and was just flabbergasted by the scale and careful thought and collaboration and creativity that was required to design something like a Blackberry. So that really piqued my interest in design. And at the same time, I knew that I was interested in going to grad school. And in my investigations of different graduate programs, I realized that MIT has a mechanical engineering pillar dedicated to product design and development. So luckily, again, for me, I got in for my master's and stayed on for my PhD before I came back here to the University of Toronto, to Canada and the University of Toronto to start as a professor. And so I teach across my affiliations. If you're a mech, maybe you took MIE 221, the Introduction to Manufacturing course. I now teach that course with Professor Benabib. I also teach a 4th year industrial engineering course called Organization Design, which is quite a bit different, but still neat, still design. And then I teach a graduate course in design in this new institute called iStep. So I have a really great research group. I think that's one of the best parts about being at the University of Toronto. It's our ability to attract bright young minds to work on research along with us. We call ourselves Ready Lab, and we study collaborative methods and tools for engineering product design. And so we have a couple different foci right now. One of them is computer-aided design, or CAD, which is what I'm going to focus on today. But we also are studying a new technique called model-based systems engineering, which is a new technique used in more commonly in the aerospace and complex systems development industries, where there's many different models from many different disciplines that need to speak together well. And using MBSE helps us to integrate those models better. And then we also have studies that look at modern enterprise communication platforms, something like Slack or Microsoft Teams, which very much change the way teams of engineering designers are collaborating and sharing information and communicating. And so we're studying ways to more efficiently use those platforms for design. So I want to just start a little bit broadly and talk about why I think there's a high potential for improving digital tools for design collaboration. I'm a little bit rare as a mechanical engineer who studies digital tools, but I think there's good reason for this. I think there's high potential that if we get digital tools to be better, we'll make collaboration better and ultimately we'll make design better. So even before COVID-19, which disrupted the world in many ways, there was a changing technology landscape. So quite recently, there have been massive step changes, increases in the computing power available, the network speeds, access to the internet. I have a big long list here. You all know artificial intelligence, robotics, cloud computing. All of these technologies have been changing the way that work in many industries get done. And in fact, these technologies can facilitate non-traditional models of work. This was true before COVID, but then suddenly COVID hit. Many of us had to stay at home to do our work there or become more distributed. And in fact, we really leaned on these technologies and these non-traditional models of work during that time. And for many of us, actually, that our work has stayed that way, more remote. And I know personally at that time, we kicked off a study where we talked to engineering hardware designers about their attitudes around working from home. And a lot of them had an initial skepticism about whether it was possible. But we also found that many of them found ways to make it work at home. And this was true in the press as well. So I found it really interesting to read about different engineering teams who we would expect would need to be co-located in the office working together, who because of COVID were forced to find creative solutions that actually really worked for them to continue innovating and designing and developing new products. Everyone from NASA's Curiosity rovers, operation teams, to Mercedes-Benz design engineers, to Boston Dynamics, who work on their crazy robots. And so I'm going to talk a lot about tools that allow us to do design in a distributed way. And maybe not all of you on this call have had exposure to those tools, but I want to start with a bit of an analogy, which maybe is closer to home for most of us. So I'm going to think that more of you have collaboratively worked on writing a report, for example. So, of course, we all know the trusted and true traditional Microsoft Word, but increasingly we have the option to use cloud-based tools like Office 365 or Google Docs, where we access these tools from a web browser. Many people can access them at once, contribute at the same time. And so hopefully I'm going to just walk you through an example of how these two experiences might differ. So one thing we think about on engineering design teams is management of collaborators and our ability to do this work in parallel. And so in traditional Microsoft Word, really it was one person at a time who could make changes. And we also found that it can be challenging to manage external integration. So maybe I'm talking about from an academic perspective here, but if you wanted to work with a citation management software tool or something, if you had it, but someone else didn't have it, sometimes there were incompatibilities and it was a bit challenging. But in general, with these cloud tools, anyone with the link can work on the document, and there's solutions that exist for integrations that make things more seamless. When we're working collaboratively on traditional Microsoft Word reports, we often need to manage conflicts and versions, and we need to do it ourselves. And so many folks have figured out their own improvised check-in and check-out systems. I know I still do work in the traditional way, and when I work with my collaborators, I'll email them and say, okay, here's the attachment. I'm going to work on it this afternoon, and when I'm done, I'll send it to you, and then it's going to be Tucker's turn, for example. So we can figure it out, but it's not so seamless. Whereas, again, these cloud tools, they tend to auto-update, they manage conflicts pretty well. Now, traceability is important in a lot of engineering contexts. Because we only have one person at a time working on a Microsoft Word doc, traceability is easy to follow and controlled. In the cloud setting, it kind of depends. So technically, we have traceability everywhere, but it can be difficult to navigate. I don't know if you've ever been in a Google Doc before and more people are popping in and they show up as anonymous animals. You know, you don't even know who necessarily is in that doc with you. That can be a little bit chaotic. And finally, sometimes we don't only want to contribute to the document, but we want to engage with our collaborators. And traditionally, we could do that with comments and emails. But in cloud platforms, we can do it in real time. Often there's a chat function, or we can even chat in the document at real time. With many people in there at the same time, it can be fun or it can be frustrating. So again, if you had the experience in Google Docs before, maybe you've noticed, a new cursor appears, someone else, and then suddenly a second cursor and a third cursor and a fourth cursor, and we can get a little bit overwhelmed with these cloud tools. So there's an upside and there's a downside, and that always proves to be an interesting research question for us academics. So I noticed that not only were, especially my students wanting to use these cloud tools to write their reports, but I also noticed that many types of work are actually moving to this multi-user cloud, meaning these things are mostly hosted on the cloud, not on a local server, So you access them via the internet, and they're collaborative architectures. So we just talked about Google Docs or Office 365. Maybe you've heard of Figma, which is a rival to Photoshop for interface design. If you write using LaTeX, there's Overleaf, there's GitHub, for programming. There's even Miro boards online as a virtual collaborative alternative to whiteboards. And so all of these are multi-user in real time, and they're collaborative. So reflecting on this, I got to wondering, what about engineering design tools? Are we seeing the same trend in that context? And what does it mean for these tools to become cloud collaborative? Do we know best how to harness this new technology? And so the first place I decided to look was to think about this in the context of computer-aided design tool. So in case you don't know, or you need a refresher, so what is CAD? That's the acronym for computer-aided design. It's a software package. Maybe it rings a bell for you. Some of the proprietary names like SolidWorks, CATIA, NX, Creo, Inventor, AutoCAD, or more recently, Onshape or Fusion 360. And these tools are used to help us generate 2D and 3D representations of a part to be manufactured. So here's just a picture of what the user interface looks like. We start with a truly blank slate. We slowly draw two-dimensional drawings, sketches we call them, of the part that we're looking to eventually build. We use a number of operations, such as extrude, for example, to build those 2D drawings into 3D shapes. And eventually we move from sort of like a crude, low fidelity version of the product that we're building to a higher fidelity one. And we can do all sorts of changes. For example, here we're adding fillets to some of the sides, edges of our part. So this probably looks familiar to some of you. In fact, what I talk about is mechanical CAD specifically. In fact, CAD is a tool that's used by civil engineers and electrical engineers as well. But since I'm a mechanical engineer, I focus on mechanical CAD, and I just call it CAD. So I think that CAD is at the heart of modern engineering design. I just mentioned that it's not only unique to mechanical engineering. I forgot to mention that architects also use CAD a lot. CAD has been around since the 1960s. It's evolved quite a bit since then. This is an example of a crash test that's part of a Tesla demo video, and this crash test simulation is only possible with CAD at its core. I think this designer over here is doing some finite element analysis, which again is sort of a sister operation of building a CAD model. And so designers can use CAD in a myriad of ways during their design process. They can explore design ideas, visualize concepts, document the design with dimensions. CAD is used to create engineering drawings. Perhaps that was like its initial raison d'etre, replacing draftspeople. You can use it to create a digital prototype, to create renderings, to simulate how a design works, or to generate instructions for manufacturing or assembling the design. And I think CAD is, again, increasingly important because of its links to, for example, additive manufacturing and 3D printing. CAD is the input file for that type of manufacturing, but also digital manufacturing more broadly. Any CNC work or many manufacturing operations are getting digitized, and CAD is the input there. CAD models can be used as the input for advanced simulation, digital twins, building information modeling, mass customization, and then they can be integrated with augmented and virtual reality in really interesting ways. And again, just in case you need a reminder of the CAD platforms you may have used, interestingly, the CAD industry is a little bit of an oligopoly where there are really four big players: Autodesk, Dassault Systems, PTC, and Siemens. And so you see one CAD system, honestly, they all look relatively similar. And these are the companies that are making those products. So again, I mentioned that before CAD, we would see rooms of draftspeople working on creating detailed engineering drawings. And CAD as a software platform evolved to essentially replace this tendency, this requirement in the engineering design process. And so it revolutionized design. It has this dynamic ability to help users create complex representations of the concept that become the blueprint for the design and the manufacturing of that part. So lots of upsides, but as far back as the inception of CAD, some have pointed out the downsides to this digital revolution. And one of the big criticisms and downsides I've tried to summarize with this picture on the right, which is the contrast between a drafting room where we have designers moving around, talking to each other, and this new way of working, which is quite solitary, solo, individualistic, as if someone has blinders on as an engineer. And so I've gone back and read some of the older work that came up at the introduction of CAD on personal computers. So in fact, this paper, CAD, Do Computers Aid the Design Process After All? It's from 2009, but it has quotes from the 1990s, which I find quite interesting. Some of those quotes are, for example, educators worry that their students will not have their experience of collaborating over drawings with peers and teachers, bouncing ideas off of each other, and soaking in new design approaches and visual thinking. Instead, the new design culture in a classroom may be one that is individual, solitary, and focused mainly on the student interacting with the computer screen. And this certainly would be a worry for me. I fundamentally believe that collaboration is required for design, leads to more creative design, higher quality design. And so I think this was a real concern with CAD, especially CAD in its traditional form, like the traditional Microsoft Word version. But what's interesting is that just like the other software platforms that I talked about, CAD is finally just now moving to the cloud. And so I think that this cloud-based multi-user collaborative CAD actually warrants a revisiting of this critique. So my question is whether we can get back some of the collaboration that we lost when CAD became so individualistic with this new cloud platform. And so indeed, there's now commercially available tools to help us do multi-user collaborative cloud CAD. And there's a number of reasons that CAD needed to modernize. So everyone was starting to realize that their word processing tools and other tools were collaborative, but the CAD tool that they spent a lot of time in every day was falling behind. There was not enough collaboration capabilities. There was poor versioning. So if you've ever worked on a collaborative team, maybe, for example, building a file that you wanted to 3D print together, this improvised version of versioning where you underscore 3D print underscore v4 underscore Alison underscore NP. The joke is sometimes say underscore use this one underscore no, don't use it, use this one. Anyway, versioning can be hard in CAD. Licensing can be really clunky. I found this meme online. CAD licenses are quite expensive. So if you had 5 people working on CAD, maybe your company only owns 2 licenses. And so you'd have to ask your colleagues to released the CAD license before you could log in. And then there's a ton of compatibility and interoperability issues. So as I mentioned, those 4 companies have a bit of a incentive to make their CAD platforms not work across with each other. And again, already mentioned this, but the tech was ready to help CAD improve. So the CAD companies and mechanical engineering users had noticed this. It turns out also that computer scientists had been noticing this recently. So this is the communications of the ACM magazine, one of the big computer science magazines, October 2021. Here, an entrepreneur named Jesse Frizzell is putting forward this argument that we need a new era for mechanical CAD. And so in the past 5-10 years, these new platforms indeed have emerged for CAD. They're called multi-user or multi-tenant cloud CAD platforms. My lab helped me make this screenshot. This tool is called Onshape. It's one of the cloud CAD platforms. You could imagine, a user in Toronto, user 1 on the left, and user 2 could be in Hong Kong, for example. And just like when we're typing in a Google Doc, a change to the right that the designer on the right makes shows up almost immediately to the user on the left. And so we can make changes to the same part in real time, simultaneously editing at the part level, which is pretty darn cool. But again, this inspires many new research questions for someone like me. I mean, it's a very different way of working. I talked about how CAD became very individual. That means we're used to not being interrupted. We're used to our way of building things. All of a sudden now we have to see if designers are compatible with each other or less compatible with each other when they're collaborating. We need to think carefully about when the right timing of collaboration is. What's the right team size? What's the right balance of skills on a team? And so all of these questions were quite interesting to me, and we decided to kick off a research program to investigate. And just a little quick note, actually. So Onshape exists, as I said, and they, in fact, sponsor some of my research. And so when COVID hit, I'm the faculty supervisor of the University of Toronto's Spark Design Club. They're a club that builds from scratch arcade games that they put around campus. You can see one in the lobby of the My Hall right now. They also put them up in Bain. And so suddenly during COVID, this team wasn't able to stay in Toronto working together. Many of them went home to where they were from, and they wanted to keep progressing on their arcade game design. And so I asked Onshape if they could share some licenses for these folks, and they did. And so it was super cool. So we ended up seeing 9 active users on this team from across North America and across the world, continuing to build their arcade game, which they could get back to when they got back to campus. All right. So just a quick fast forward, I guess, to what we do in my lab in terms of how we aim to influence the design process. We actually aim to improve design with 3 different user groups. So first of all, with CAD users, trying to establish best practice for them to be able to collaborate better. We also work with CAD providers. So are there different features in the software or features that could be changed in order to enable improved collaboration? And then finally, we're working even here at the University of Toronto with a couple of different courses where CAD is instructed to help develop better learning materials and to understand best practice for how to learn and collaborate with CAD. Okay, so I want to bring us back to this view of CAD, right? And just to remind you that, in fact, individualized design work is actually the opposite of what we need in design. So today's products and projects are getting more and more complex. often more multidisciplinary, and one person is just not able to have the expertise needed to perfect the design. Timelines are getting shorter, automation is becoming powerful, so we need the designers to do the creative thought. And so collaboration is really increasingly important. And so although the reality of CAD maybe 10 years ago was this way of working, I wanted to know, does this have to be true for CAD? And so my lab undertook projects to explore new ways of collaborating in CAD. So the first place we decided to look was to software development. I mean, the easiest way to study collaboration is to study collaboration between two people. So that's where we started, with pairs of people. So if there's any software developers on the call, you've probably heard of a technique called pair programming. That's where two people sit down together at a computer. That's how it was originally conceived, at least. One person is called the driver. They're sitting with the input devices, and the other person is called the navigator, and they might be looking at the project requirements. We're also looking at what's being coded on the screen, looking for logical errors or any type of errors. And the idea of the driver navigator is that it's like two people sitting in the front seats of the car. There's the driver, and then there's a navigator. And so this has been a successful means of learning to code, onboarding people into new organizations to understand the best practice at that organization. And it's a part of, it's often seen as a part of agile software development, if you're familiar with that. Though it started with two people sitting together at one computer, it's evolved to also be to have a configuration called remote pair programming, which shouldn't really be surprising, right? Nowadays, we can have video on, we can share screens, and so we can do this sitting beside someone or sitting on the other side of the world from someone. And so there's been studies by software engineers about the outcomes of pair programming. And in fact, those studies have found that when you work in a pair programming configuration, your code has fewer defects and higher quality. Your two coders end up with enhanced learning. And the two coders also have a better affect or higher satisfaction. And so this was quite inspiring for us. We're wondering, okay, those are neat outcomes for code. Is the same thing true for CAD? So I'm going to talk about two different studies that we've done. One to look at product quality, pair CADing and product quality. The other one to look at pair CADing and designer emotion. So here we run experiments where we invite designers into our design lab and we record them. We record their screens. Sometimes we record their faces, or we use eye tracking. We have like a highly instrumented design studio here in the My Hall building, where we can have novices or expert designers design, and we can collect every click that they do while they're doing it. And so this study was with a number of great collaborators highlighted at the bottom. And we decided that we would look at three different configurations. So one, as sort of like a control, we had folks just doing our design task as individuals by themselves. Then we introduced two different types of paired collaboration. One was parallel CAD, which is truly like a Google Doc, where two people can be working in parallel, but in real time. They're not looking at the same thing. They can be clicking in other places, but they're using that cloud CAD platform. Actually, so is the individual CADer, so that we could compare apples to apples to apples. And then we had a shared CAD configuration where only one person could be driving at one time. So really reminiscent of that driver navigator scenario. So they had two screens, but they would be deciding between themselves who was driving and who was navigating at any given moment. We brought in 60 participants to do this experiment overall, and our participants were randomly assigned to these different configurations. And when our pairs were working together, they had a headset and mic, so they actually weren't sitting side by side, but they could communicate via headset and mic. So we were really emulating a work from home setup. So we used this CloudCAD platform Onshape, and what we decided to do was design a task for our participants, which was based around change requests. So imagining that our designers were working on a cell phone holder and they slowly progressed through a series of change requests from their boss, for example, based on design reviews. And so these are just 3 snapshots along the way. It starts with quite a primitive phone holder, and eventually you're adding features little by little until you get to the very end with this cell phone holder on the right. I don't want to get into too much detail here, but I mentioned that we're measuring quality of the output CAD models. It's hard to say right off the bat what makes a high quality CAD model, but luckily other folks have been thinking about this carefully. So we used their way of thinking about quality, which was to see completeness, concision, consistency, and validity. So we used a quality metric from the literature. And I'll get right to our results here. So we looked at speed per person and model quality. And so remember, we had individual CAD, parallel CAD, and shared CAD. And so right off the bat, we can see that speed per person. So we have averages and we have, I think this is quartile ranges. I actually don't exactly remember. We can see some interesting results. So individuals, it turns out they are, in fact, when they're working by themselves, faster than pairs working together in either configuration. And it turns out that if you look at the collaboration literature, this is not all that surprising. There's something called collaborative overhead. If you imagine you're working on a task with someone else, you're not 100% dedicating your time to that task. You have to communicate together and coordinate together, and that takes away some of your pure productivity time. So we weren't surprised to see that individuals were in fact faster than pairs. What we saw over here was that the shared CAD by a smidgen was the highest quality output. So we say 4 eyes are slightly better than 2. So the quality of those models was higher than individual CAD and in fact much higher than these parallel CAD where 2 people divide and conquer and go off and aren't necessarily coordinating or working together. What we did notice was this tighter distribution on the quality of the shared CAD performers, which really might matter maybe even more than this slight difference in overall average to a design engineering firm. So with 2 people, again, we can catch more mistakes. We can make sure that we don't have a low quality tail way down here. We have a tight distribution of high results. And why might that be? So same thing, when we take a look at the collaboration literature, we see that there's some discussion of something called a social pressure for diligence. So when you're working by yourself on a task, you might be tempted to move along pretty quickly. You might only have your own standards to which to hold yourself. But when you're working with someone else, that social pressure might increase your tendency towards diligence. And so you might be raising your bar in terms of the quality that you're looking for. An interesting finding there. But we were certainly still interested in these second set of features of that software developers who use pair programming claim, which is that the experience of designers is more satisfying when they work in a pair. So that's what we looked at next. And to do this, we're actually linking emotion to behavior. So this was a neat study where I learned quite a bit. We went back and learned about the emotion theory. And so there are different ways that psychologists think about emotion. But one of them is to think about emotion in 2 buckets, negative emotion and positive emotion. So in fact, when we experience negative emotion, it signals threat to us and it signals that a change should occur. So it, in fact, elicits effortful, systematic, and detail-oriented information processing strategies. Whereas if our body experiences positive emotion, it signals that the status quo can be maintained. It elicits simple, novel, and creative information processing strategies. And so if you've done engineering work, I'm sure you can recognize that sometimes we need effortful, systematic attitudes, and sometimes we need novel, creative information processing strategies. So it's quite interesting to think about how we likely need a balance of these emotions. And so we decided to take a look at the discrete emotion framework, which if you've seen the Pixar movie Inside Out, it's what they based those characters on, which is a simplification, but recognizes 7 different emotions that we experience as humans. So again, we collected data with designers in our lab. Here, I'm going to focus on the facial recordings of our participants. And we also took screen recordings as our participants made it through their task. Again, we used Onshape here to facilitate cloud collaboration. And so we used a neat technology to go from the recordings of our participants' faces to this emotion data. It's called Affectiva. And it uses facial recordings. It detects a face, and then it extracts key facial feature points. So see, it's pinpointed the edges of this person's eyebrows and their cheekbones and their mouth. Once it's pinpointed those locations, it tracks them and sees how they move together, and has claims to use advanced machine learning models to convert those measures into emotion. So this is something called facial action coding system. In fact, before machine learning, individuals would be trained to do this, and it would be painstaking work to watch a video and to look for emotion there. Now we can do it frame by frame. And so this is a real recording from our experiment. You can see on the left, one of our participants, he does look pretty darn surprised. Maybe his partner has made a change in the model he wasn't expecting. And when we look at that same time slice, we see that the intensity of surprise peaks. So pretty neat to see that our gut instincts when it comes to emotion were reflected by this Affectiva output. And we also used cursor detection to see where our participants were working in the CAD UI at any given moment, but I'm not going to get into this too much, so I'll keep moving. So it's quite interesting. This is one of our screenshots. Notice that this participant is typing over here in the chat window and experiencing quite a positive emotion. What she's typing is, now we have some dope headlights with the new height. So I forgot to mention that here the task was designing a toy car. It turns out what we found quite interesting was that participants laugh not only at their partner's jokes, but also we laugh a lot at our own jokes. We knew that was true as professors. Now I see it's true in the general population too. So we crunched all the numbers and looked at emotion in all of our different categories, compared our singles, again, we had participants working by themselves and participants working in pairs. And what we saw was that pairs experienced, on average, per person, higher levels of emotion, both positive and negative, than individuals. So you can see that pairs had more surprise, more contempt, actually not more disgust. And this is an interesting finding that we're not exactly sure how to explain. More anger, more joy, more sadness. And so why do we think this would be? Well, we think that most of our participants, because of how new CloudCAD is, are used to designing by themselves, being fully in control of their file, and all of a sudden they've lost that control. And so that would explain a lot of surprise and contempt, perhaps. It could be frustrating to see someone else making changes here. It turns out that the emotion literature talks a lot about how other humans are high emotion evoking stimuli because humans tend to be unpredictable. And so quite interesting that we found this here too. And I believe that this confirms the finding of pair programming because emotion, whether positive or negative, tends to lead to a more engaging experience. So this is good news, I think. We like to work with other people. CADing can be a solitary, dare I say, even boring experience. And so I think opening up to the world of pair CAD could open up a way to make this job more engaging for design engineers. And so I think that modern cloud CAD tools can potentially bring collaboration back to designing with CAD. And we really can take inspiration from the way that software developers have been coding. And so we published these findings that I talked about. If you're interested in reading a more academic perspective, we coined this term pair CAD, and we have a couple journal papers on those topics. Okay, so what about collaboration in CAD beyond pairs? That's what I'm interested in thinking about now. And it turns out that we have another great faculty member at the University of Toronto. Her name's Shu-Rei Zhou, and she is a leader in understanding collaboration in GitHub. And so she and I have partnered up, which is really neat. I'm learning a ton, along with our great PhD student, Kathy Cheng. And we're doing a study instead of based on experiments and lab-based studies, we're actually going out into the world and talking to real designers and understanding how collaboration happens with CAD. And so we've recently published a paper in the Computer-Supported Cooperative Work Conference, which we titled "In the Age of Collaboration, the Computer-Aided Design Ecosystem is Behind: An Interview Study of Distributed CAD Practice." And here we talked to 20 CAD professionals from a bunch of different industries and roles and experience levels. And we universally heard that collaboration is a barrier to effective CAD. And so what we heard over and over and over again is this type of a scenario. So this is just about version control, one element that doesn't work well in CAD. So let's say you're a designer, you're asked to make an update to an important document at work. You go find that document in a shared database and make the updates that are needed. But when the update is reviewed, you discovered an issue. Little did you know, the file you downloaded from the database was not the most recent version. The most recent version was on someone's local computer. Plus, while you were making your recent update, one of your other colleagues had found a different issue and was updating too. So we had a big mess. There's 3 different versions floating around with potential conflicts. This happens in CAD all the time because of different stakeholders like the marketing team, the manufacturing team, the quality assurance team. And so I found it interesting. I took a look on Twitter/X for the keywords version control for CAD, and it turns out like everybody wants version control for CAD. We need to get better here. And one of the most popular means of version control in software development is branching and merging. And so Professor Joe from ECE and Kathy and I are looking at branching in computer-aided design. That's our first paper. Next, we'll look at merging in computer-aided design and thinking about why this is important. So branching can help us, we think, manage the product line, isolate risk, and to support designers. And in this paper, we go through and talk about each of these use cases, and we draw parallels to software development and try our best to learn from what they're doing there. All right, so that is a whirlwind tour of a little bit of my research. I want to talk about what's next. What's next and ongoing, I guess, is establishing these best practices for collaboration in CAD. So far, we've looked at quality, we've looked at speed, we've looked at designer experience collaborating. We haven't looked at creativity, partly because creativity is such a hard thing to look at, but it's time. And so we're curious how CAD influences designer creativity compared to other design tools, especially if it's used for early stage design. Another research direction that's important to me is in the realm of engineering education, thinking about how can we better level the playing field for all new students to have confidence in CAD. What we see in practice is that some students maybe who went to a well-resourced high school or who have family members with more engineering experience, learn CAD in high school and build those skills. And when they come to the University of Toronto, they have really high confidence, which is awesome. But if there is group work where CAD is one of the deliverables, those folks tend to work on that group work and kind of like hog the CAD work, which leaves the learning experience behind for others. And we tend to see this happen where young men get that CAD experience in high school and women don't. And so there's lots of girls who code programs. We're interested in starting some girls who CAD programs. And then finally, again, this is just the CAD slice of my work, but we're certainly interested in continuing to think about tools for communication during design. And also we have some projects about new approaches to design like hackathons and understanding how design works there. And so you're welcome to email me or find me on LinkedIn. I'd like to connect. You can find our papers on our website. And again, just a great shout out to my research group who've contributed so much to all this work that I presented today.
First of all, thank you to everybody in the audience for your questions today. Before we close, I want to thank Professor Alison Olechowski for being with us today. I can say that we had a record turnout of online participants. Typically, we get 50% or more of the advanced registrations who actually join us online. And we had a fantastic number of questions. I didn't have to revert to the questions in advance. There were questions were bombing in online during the course of the presentation. So thank you again, Alison, for the informative presentation on how in-program collaborative tools can positively impact mechanical engineering product design. To everybody who joined us here today, and it was a record, we invite you to share your feedback on the Skule Lunch and Learn series. A link to the online survey is being made available in the chat function at the bottom of your screen, and will also be shared with all of you after this event by email. A link to the presentation will also be shared with all registered guests early next week. The Skule Lunch and Learn events are traditionally hosted on the second Wednesday of each month from October to February of each year. Today's presentation, unfortunately, is our final event of the 23-24 Skule Lunch and Learn season. However, we look forward to resuming the new season once again in October of 2024, and we'll be sharing more details about our upcoming speakers later this summer. So in closing, I would like to thank all of you for joining us today for the presentation, and hereby adjourn the last presentation of the 23-24 Skule Lunch and Learn season. Thank you and have a good day.